Okay, good afternoon. My name is Grigory. I'm from Team Ukraine, and today I'm going to report the solution of problem number 3, dirty racing. According to the statement of the problem, we have to investigate the deceleration of the metallic of the balls which are rolling on over the sand surface. Define the distance the ball travels before it rests, and depending on different parameters of the sand and the surrounding. In my report, first of all, I will give a qualitative explanation of this effect, in which we will describe this deceleration process, on which parameters we think it depends, and we will describe the different types of the motion, depending on, as I said, different parameters. Then we will give a theoretical explanation of this phenomenon, investigation of the distribution of pressure, of the sand below the ball, and investigate the motion of the ball itself, writing the equations of motion. Then we will move on to our experimental investigation of this phenomenon, in which we will construct an experimental setup and investigate different parameters. First of all, let's start from the qualitative explanation of the phenomenon of the deceleration. It is caused by the effect that the ball, instead of the case when it comes to the rest, in our case it rolls, thus it creates some kind of cavity, and thus the overall force which acts on a ball becomes not vertical, it has also a horizontal projection, and this horizontal projection decelerates the ball. Here you can see our experimental videos of the motion of the balls on a sand with a different humidity, with a different concentration of the water. And here you can see that in the case of lower concentration, the ball decelerates not as fast as in the case of high concentration of the water. And to describe this effect of the motion of the ball, we are going to theoretical investigation of this problem. And start with the distribution of the pressure in the sand. It is a problem which is related to the investigation of the sliding inside the granular materials, which is well known in literature, in which the stress, in which we have the stress tensor, which has only diagonal pressure components and the friction components according to the Coulomb's law in some frame of reference, in which the sliding occurs. This frame of reference is described by some angles theta and phi in the three-dimensional space. And to return to inertial frame of reference, we use usual law of the change of the components of the tensor, and in this frame of reference we write the Euler equation, which is the equation of the equilibrium of this elementary fragment of the sand. Knowing this, solution of this equation gives us distribution of pressure and distribution of the angle theta and phi in which the sliding occurs. And here you can see the example of such a solution in our case, where we investigated the pressure distribution under the ball. And you can see that under the ball, there is the highest pressure. Of course, however, at some distance, it decreases to atmospheric pressure, for example, at the surface. And at the bottom, for high depth, we see that the pressure increases due to the, I would say, hydrostatic pressure. Now, as we have found the distribution of pressures for a sand, we can investigate the force acting on a ball to investigate its motion. As a force acting on a ball may be given by such an expression, which defines the elementary force acting on a small fragment of the ball surface and integrate over its surface. However, we understand that in this problem we cannot write any kind of non-sliding condition because of the complex process of the initial motion. And to do this, to investigate this process, we also write the rotational torque acting on a ball, which we calculate from the center of the ball just by the definition of the torque integrating over the surface of the contact. And then, as we have found the forces acting on a ball, we write the equation of the translational motion and the rotational motion for a ball. And here you can see the example of solution of these equations. As you can see, indeed, coordinates. Firstly, indeed, we see some kind of behavior which looks like a constant acceleration motion, such as after some time the ball stops and doesn't move further. On this video and this animation, you can see the comparison of the real experimental video and our simulation, in which we have plotted the pressure distribution. As you can see, indeed, we can really precisely predict the deceleration effect. And now, as we have theoretically solved this problem, we can move on to experimental investigation. To do this, we use such an experimental setup in which we used sand. We used with the pen in which the sand was placed. We used a curved tube to obtain very smooth motion of the ball to the surface of the sand, to prevent some kind of heat in it and losing of energy at the initial stage of the touching of the ball in the sand. And then we have smoothed a surface of the sand using a cylindrical roller, using which we obtained a really smooth surface, which allowed us to provide an experiment in very straight conditions. And also we use different type of balls for which we investigated the dependence of different parameters leading to the deceleration of the ball. To analyze the motion of the ball, we use a program tracker. And here you can see different different dependence of the position of the ball on time for metallic balls represented in a photo previously. As you can see, for them, we observed different trajectories. And for one of this trajectory, we compared the theoretical result with the experimental one. And you can see that our theory indeed really good predicts this deceleration process. Further, to investigate more precisely the different parameters, depending on how does different parameters affect the overall motion, we, for each experiment, made such a histogram using which we investigated the mean value of the path distance and the dispersion of this value, which allowed us to find the experimental uncertainty very accurately, and also to find the mean value with high accuracy, not just based on one experiment. First of all, we investigated the role of the mass. As you can see, we investigated such balls represented here. As you can see that for the deceleration of the ball at the initial stage strongly depends on the mass, and there is an optimal value for a mass, which is correspond to the effect that for small mass, they have a really low inertia, and thus they strongly decelerates because of the friction. However, the massive balls creates a very deep cavity, leading to the increase of the deceleration force, and this effect leads to the appearance of the minimal value. The second criterion which we tried to investigate was the concentration of the water. And however, as you can see, our theory predicts a decrease of the path distance. However, in the experiment, as you can see, for example, at this video, as we try to use a concentration of nearly 6%, we observed that the velocity of the ball strongly increased, and also there doesn't create any cavity after the ball. And to investigate this effect, we understand that the effect reasons for this uncertainty is cohesion. And to add the cohesion, we just change the tension tensor. However, the equations which we solved were the same. And to define the cohesion constant, we used such an experimental technique described in literature, which allowed us to find the cohesion coefficient depending on the concentration. And now theory really good predicts the initial stage. However, the final stage, our theory do not predict because of the more complex motion of the ball in this substance, which becomes more viscous, I would say. So in our investigation, we first of all gave an explanation of this phenomenon, theoretically described it and experimentally, and verified it for different parameters of the system. Thank you for your time.
So could one of my teammates just help me share my screen and I'll just continue talking. So hello everyone, my name is Yansheng from the UK team, and now I'll posing question number 3, dirty reason. So first I'm going to start with a summary for the question. So for the presentation, so the reporter started by giving some qualitative explanation for why the rolling of the sand would experience some friction. The rolling of the ball on the sand would experience some friction, and the qualitative explanation is very good. So the reporter explained this in terms of the indentation of the ball made by the sand surface, and I would very much agree on that. And then the reporter went on to give a very comprehensive theoretical model using continuum mechanics and consider both the coulombic friction and the cohesion due to the surface tension of the water later on. And then the calculations are rigorous, and we see some of the theoretical plots as well. And then the reporter gave a very comprehensive experimental investigations as well with many different parameters, and the results do show pretty decent agreement with the theoretical model. So overall, I think the reporter has done a good job, although there might be still some small areas of improvement, which I would like to discuss next. So for more details, I will now go into the strengths and weaknesses for the report. So for the strengths, I would like to again commend the reporter for giving a very good qualitative explanation for the phenomena. And the theoretical model is really rigorous, and the experiments are really comprehensive with many different parameters, varied. Also, I would like to congratulate the reporters for getting a good agreement with the theory from their experimental data. And finally, I will really commend the reporter for doing a very rigorous quantification for the errors in the data by using a histogram to estimate the standard deviations in the maximum distance rolled by the ball. And finally, the reporter has done a good job in characterizing both the cohesion coefficient and the friction coefficient using the angle of repose instead of using them as a free parameter. I think this is a very good approach, and that makes the justification for the theory more convincing. However, there are some areas of improvement which I would like to talk about. So the first, I take a bit of problem with the method the reporter releases the ball. The ball is released directly from a tube into the surface, onto the sand surface, and this is slightly problematic because the tube, at the end of the tube is not exactly parallel with the sand surface. That means that the ball will actually hit the sand surface with a vertical velocity, and this vertical velocity is going to make some indentation, which may make the ball harder to roll at the start. And also this indentation is an unintended effect. It's not really what we want to look at here. So it's the best to just avoid it. And in some cases, because of this vertical velocity, as seen in some of my own experiments, the ball might even bounce at the start. And all those are complications we would very much like to avoid. So I think this point should be looked at. And I think dealing with this problem is actually not that hard. We could release the ball from the tube, and to prevent the problem at the start, we could let the ball roll on a flat surface for a while first. And this could also help to ensure that the ball is in pure rolling motion before it goes into the sand, and that will help to simplify some of the theoretical part as well, because thinking about all these complications due to the not very well controlled release of the ball is not really what we are most interested in this question. And next, I clarified with the reporter just now. The reporter it seems that the reporter has not considered plastic deformation in the model in the sand. Although I think quite clearly the sand does deform very plastically, and I think most of the energy loss is by plastic deformation because we can clearly see the indentation on the sand. And this is something I would like to clarify with the reporter later, just in case I misunderstood their model. And next, in terms of water content measurement, I will commend the reporter for measuring the water content, but I think this needs to be done quite carefully because if you just use the sand as it is not completely dry. So to get a very accurate measurement of the water content, you must pre-dry the sand by heating it in an oven to drive out all the water that's already present in the sand when you get it. This is because we have some level of air humidity in the air and some water is going to condense in the sand. And this is particularly important if the sand is if the grains of the sand is very fine, and it seems to be the case, judging from the experimental images, that the sand is very fine grained. So in this case, the sand itself, before you even add water, could potentially trap a significant amount of water inside, and that could change something, and that could change the x-axis. Though I do not think this would directly impact the data because to generate a prediction, the reporter actually measured the cohesion coefficient instead of predicting it from the water content. And next, I think an important property that's not discussed here is the granularity of the sand. So how fine the sand particles are. If we're dealing with very fine sand versus very rough and very rocky sand, I think it's going to make a very important difference. And this is the point I would like to discuss later as well. And finally, I think when the sand, okay, so this is pretty much it. And the first point of discussion, I just want to clarify again, is plastic deformation explicitly considered in the model?
No, as I mentioned, in our model, we consider the deformation of the sand used by the Coulomb friction model, which is well known for the granular materials such as the sand.
Okay, so I think that's correct. That's correct if the plastic deformation is small, but in some of the cases, we do see a very clear indentation. So in that case, we do need to consider plastic deformation. And I think the importance of this factor depends on the particular regimes which we are looking at. For example, if we are in a moderate water content regime, then what's going to happen is that the sand is going to be quite cohesive and it's going to be quite hard to plastically deform it. Then as we see in the experimental videos provided by the reporter as well, there isn't too much plastic deformation. However, in the other two extremes where the water content is very low or the water content is very high, the indentation is quite clear. So I think in that regime, things need to be considered more carefully. And I think introducing plasticity into the model might be quite essential because quite a lot of energy dissipation could come from that plasticity. Yeah.
Okay. Yes, and I understand the question that the elementary particles in a granular material may be in some way plastic. You mean this?
Yes, definitely exists plastic deformation.
Yes, I understand this question. Indeed, in a case of some granular materials, which in some way plastic to external deformations, it has to be done. It has to be added. For the sand, it is we do not have such strong pressures to investigate such a phenomenon.
Yeah, yes. So I think this might be a secondary correction because we do see the indentations on the sand, but of course it's not huge indentations. So maybe it's a secondary correction. So that's just some suggestion because I do understand that incorporating plasticity is going to make the equation a lot more difficult. Okay, I think we have reached some agreement on this point. Maybe we talk about the next point. So in terms of the property of the sand, so one very interesting property is the granularity of the sand. So do you expect changing the granularity of the sand to affect your friction, your overall friction for the ball as it rolls?
Yes, indeed. Indeed, this effect of the change of some kind of granular of elementary structure of the granular material may lead to change of the properties. In our case, the main properties are the friction coefficient, of course, and the cohesion coefficient. Yes.
So maybe we just pick one factor, which is the cohesion coefficient. So suppose I have a very fine sand versus a relatively rough sand. And at the start, they are dry, and I can measure their cohesion coefficient. And then if I add equal amount of water to both, their cohesion coefficient is going to change, right? So in this case, if I add a moderate amount of water, which sand do you expect to have a larger increase in the cohesion coefficient?
May you clarify the difference between the sands one more time?
So, the sand. So, say the sand on the left has a particle size that's distributed around 20 microns, whereas the sand on the right has a particle size distribution about 200 microns. Then I add water. Which one will have a bigger change in the cohesion coefficient?
In my opinion, the particles with the less sizes will have a higher cohesion coefficient because of the cohesion because of the distance between the mean distance between particles is lower, and the surface effects leads to stronger cohesion.
Yes, I would agree on that point. Although I will try to explain a bit more carefully, because the reason why we get cohesion in the first place is that water can form capillary bridges between grains. Is that right? And then if we have very fine sand, there are very extensive contact areas for these capillary bridges to be formed, and this bridge network can be very strong. And in fact, we can get very strong strengthening or very strong cohesion in that case. And in contrast, if we have very rough grains, then the separation, on the one hand, because of the less efficient packing, the separation between the grains are likely to be larger, then capillary bridges are harder to form, and also the surface areas the surface interaction is less extensive, and that's why the cohesion overall is going to be a lot less. And I hope this is the interesting point.
Yes, indeed, I agree mainly with you.
Yeah. So this is it. So we had a good discussion on that. And finally, and then an additional point I want to bring up is about surface tension. So did you consider surface tension in your model in any way?
The surface tension, the effects which lead. I want to reformulate your question. You mean the effect of the surface tension on the motion of the ball directly, or in some case of the properties of the sand?
I'm thinking more on the line about the motion of the ball.
Yes, now I understand your question. In our model, we didn't consider it because of the main effect, like it is not the main effect which comes from the increase of the concentration. In our opinion, the main effect is some kind of different friction because of I want to say viscosity, because the sand with a high amount of the water behaves like water, like a liquid, and this changes the type of the friction. And because of this, we do not consider that surface tension may strongly affect this phenomenon in the case of a high amount of water. The main effect is the change of the friction type. I want to say it so.
Yep, I might want to slightly agree on that. Disagree on that point, because as much as we can have cohesion between sand particles, with water we could potentially have cohesion between the sand and the ball. And in fact, in some of the experiments, I think in one of the videos with very high water content where the sand looks very saturated, as the ball rolls, some of the sand is even thrown off of the ground by the ball. So that's, I think, a pretty clear indication that there is quite significant cohesion between the ball and the sand because there's surface tension holding them together. And that could potentially be an effect that's important if we are looking at very high saturation. But of course, I would agree that modeling that is a bit ridiculous to expect people to model that. But nonetheless, I think this is an interesting point which we could bring up. And then in the end, I think we still have some time left, and then we might want to think about one more question. So I think in your plot, you have plotted the maximum distance that can be reached across different water content. So I think you went through that quite quickly, but could you give some qualitative explanation on why there is an optimal water content for minimal friction?
Yes, I will explain it one more time. The reason is that sand becomes more not dense, it becomes very hard to push the sand, and thus creates some kind of cavity because of the increase of the concentration. And because of this, the size of the cavity is lower, and thus the friction is also lower. And this leads to the longer travel distance. However, as we further try to increase the concentration of water, the whole substance becomes very, as I mentioned, viscous. And due to this effect, the travel distance becomes lower, and these two effects leads to the appearance of the optimal value.
Okay, I would agree on that. Though I would like to further discuss on this point by asking the reporter, how do you think this phenomenon? So what do you think is happening microscopically as you undergo the transition? So if we think about the interaction between sand particles, what's happening there as we go from the decreasing friction to the increasing friction stage? What do you think is happening?
Yes, it was in some way unclear. However, as we for a rough sand, we first of all add a small amount of water. Then the cohesion leads to the sticking of the sand grains one with another. However, as we try to further increase the concentration, then the average distance between particles between the sand grains increases, and thus the interaction between the sand grains changes. And due to this, they're mainly the water in the substance instead of the sand. And this effect leads to the appearance of such an effect.
Okay, I think that's fine. But the way I think of it is that if we're having a moderately low water content, then the water bridges are going to be very distinct. And it is these water bridges, these capillary bridges that are formed between the sand particles that's giving the strengthening. But if we increase the water content too much, then what's going to happen is that these water bridges are going to coalesce. And once they coalesce, the sand particles can move in a fluid. And in this case, we do not have the capillary bridges holding them in rigid positions. Instead, as the reporter has correctly pointed out, we are mostly considering viscous drags as the sand moves around as a suspension in the fluid phase. So I think that's a good discussion, and I think we're already over time. So I would like to thank the reporter for the report and the discussion.
Thank you very much.
You studied different balls with the different materials, and maybe I missed it, but have you studied the impact of the surface quality of the ball on the result of your measurement? It's hard to do because you have different masses, but do you have any considerations about it?
About the condition of the surface of the sand?
No, not the sand, the ball.
The surface of the ball. Yes, in our experiments, we had some kind of different surface of the ball. Some of them were rough, some of them were smooth. So in our experiment, we didn't observe such a significant difference between these cases.
Okay, thank you very much.
Thank you, Alexander. Okay, please.
Yes, reporter, can you show me again how the position changed over time and your theory?
Yes.
Precisely this one. Yeah, and then let's see, you had two of them at once, the experiment and the theory. Yes, that's one. So how many parameters are fitted in this theory?
No known parameter, because we know everything which we have to know about the sand, mainly the friction coefficient. The parameters of the ball are known, and thus we just compare the theoretical and experimental result.
Okay, and then second question, in your theory for calculating the braking force, how do you choose the depth of the cavity?
Yes, it is an interesting question, and the depth of the cavity were found by the equalizing the vertical force acting on a ball. Here you can see the expression for it. The equalizing the vertical force to the gravity force of the ball, which gave us the size of the cavity.
So in your theory, does the ball, does the cavity become deeper, become more shallow, or stay the same?
At the initial stage, indeed, it becomes deeper. However, this initial stage is quite short, and after some time, the rolling continues with nearly the same depth of the cavity. Okay, thank you for answering my questions.
Thank you. Okay, Jürgen, please.
Okay, can you show the slide with the results of the repetitions, where you did 100 repetitions for the same ball? The next one. So I think the next one is where you did something with the results of it before. The error bars shown here, are these the standard deviation or the error of this mean value from the 100 repetitions?
Yes, it was found from such a histogram which we investigated experimentally. And from this, we find the deviation.
Yeah, is it only the standard deviation of the 100 repetitions which you've shown here, or is it the error of the mean value?
It is the error of the mean value.
Okay, thank you. And have you changed the initial velocity and some results of that?
Yes, indeed, we changed. It is obvious that the length of the ball increases. However, mainly that didn't really depend on the velocity, it range of the velocity which we investigated.
Okay, thank you.
Thank you, Jürgen. Alexander?
Yeah, I got a quick question for both of the teams. Do you think the effect will quantitatively change if you tune the temperature of the environment, like taking like super cold sand or doing this in a very hot room? Just trying to imagine.
Okay, in my opinion, strongly like the main effect that may be observed is some kind of change of the internal structure of the sand. For example, for a sand with the water, this effect will indeed lead to the change of the cohesion coefficient. And yes, it will in some way lead to the change of the overall process.
In my opinion, there are a few factors that could lead to the changes. So if we're looking at wet sand, so for wet sand, we cannot go to very extreme temperatures because water will either evaporate off or freeze. So we just stay in a moderate temperature range. And in this range, if we change the temperature, then the key effect will be on the surface tension of the water, because the whole reason why we see this dip at the start is because of formation of the capillary bridges between sand particles, and that's giving a strengthening. So if we change temperature, surface tension changes, and the strength of these capillary bridges between sand particles is going to change quite drastically over temperature, and that's going to give a very significant impact on this curve. So for example, if we increase the temperature, if we're looking at the initial part of the curve, I would expect this curve to go down, because with less strength holding the sand particles in place, they can deform more easily, and that could lead to more dissipation and therefore shorter distance that can be reached by the ball. And then, sorry, in this case, it's a deceleration of the ball. So higher deceleration, so the curve will go up for the initial stage. And another effect for dry sand is that Coulombic friction, if we're looking at static friction, is actually dependent on the temperature. So I think people have done experiment on that by lowering the temperature to like to the temperature of liquid nitrogen in some other systems. And there's a very strong dependence on the static friction with temperature, and that could potentially play a role in the scenario here. So that's my answer.
Got it. Thanks.